Hello everyone, I'm Dan, and today we're going to be doing something a little bit different. So, I've had a lot of people ask me, how does Fusion work? I don't really understand how the internals have been set up, etc, etc, etc. So today what I thought I would do is I would walk you through the process of building up your own version of Fusion from scratch so you can see how exactly all the different systems have come about. So the version that we're going to be basing this video off of is v0.2. However, note that we already have some changes down the line that are going to change this model in some fundamental ways, but this should at least give you an appreciation for how version 0.1 and 0.2 have been put together. So with that out of the way, it's really important to talk first about what Fusion actually is, right? Because Fusion markets itself as a UI framework. But actually, if you take a look at Fusion's internal design, UI really does not come into the majority of it. Fusion is fundamentally about state objects. And I mean, you can kind of sense that based on like just how many of those you use, but really Fusion's core functionality is entirely housed inside of state objects. So that's a really good place to start. So let's say we want to store how many clicks we have. So say local num clicks equals 0. And then we want to, I don't know, transform that into a message. So say local message equals you clicked dot num clicks dot times. And now we want to change the number of clicks. So say num clicks equals 5. Okay, that's cool. But our message is not going to automatically update for us, right? If we were to print out this message, it would still say you clicked 0 times, even though num clicks is now 5. That's a bit of a predicament. So we're going to need to start building up some abstractions in order to make this work. So what we're going to do is we're going to write a getter and a setter for this num clicks. Local function get num clicks, return num clicks, and then we'll say local function set num clicks, new clicks. You'll say num clicks equals new clicks, and I spelled that wrong. And now we're just going to exclusively use the getters and the setters. So set num clicks 5. Now, your first thought might be we've done absolutely nothing here, we still have the same problem. But actually, because we are now basically promising to ourselves that we're only ever going to go through the getter or the setter to change this variable, we now have a very powerful tool at our hands. We can place code in these functions that will run whenever you get or set the value. So in this case, we'll just move this up here so we can access it easy. We'll say message equals you clicked get num clicks times, sure. So what we do here is we'll say set num clicks to be 0 here, and that will initialize the message, of course. If we were to print message after this, it would say you clicked 0 times. And if you did set num clicks 5, this would say you clicked 5 times. Very good, right? And so this is kind of a bit clunky at the moment, having these functions separate. So I'm just going to make an important change real quick. We're going to say num clicks equals get equals function and set equals function. And this is going to be an object. So we'll say underscore value equals 0. That'll be its initial value, I guess. Or, yeah, it doesn't matter. We'll just say value equals nil, because that's a good undefined value for now. So we'll just say return self.underscore_value. We obviously need to pass self in here, because we're making an object, essentially. And then new clicks. And we move this in here, move message up there, and you can see we now have the beginnings of a value object, right? And so this is a fundamentally very simple thing. Like, we should all be on board with this right now. If you're not, then you might struggle with the rest of this video, maybe take a second to brush up on your Lua. But if you're cool with this, then everything else naturally develops from here, from first principles. Right, so first things first, message right here is a bit of a nonsensical thing, right? Like why should our setter be worried about what message has to do? Right? Like this is bad. So what we want to do is, well, we want some abstract way of sort of depending on num clicks that will allow us to update ourselves in response to changes in num clicks. So what we're going to do is, well, we'll get rid of these here. So we just have num clicks now. And what I'm going to do, I'm going to create what I'm going to call a dependent set. And this set will contain references to code that we want to run when like the value is set, right? This is going to be callbacks for now. So we'll say for dependent in pairs dependent set, do dependent like that, right? If you're wondering why I'm using the keys instead of the values here for this table, this is because it doesn't make sense for a dependent to be added twice, right? Like think about how a table works. Like if we use an array, we could have like local function, I don't know, update, blah, blah, blah. And we want this to run, it's like whenever the number of clicks changes. So we're saying table.insert num clicks update. And yeah, that's fine, cool. But now you can do this and it runs 5 times, right? And that is nonsense. We don't want that. So instead of doing that, we actually invert things a bit, because values don't have to be unique in tables, but keys do. And what we want here is we want uniqueness, right? And the best way to do that is to just use the language, right? Num clicks update equals true. Right, and this is something I really hope people do more in Lua, is that they actually use proper sets, which you can do by just using keys, and I mean the value doesn't really matter, right? But what this means is that there will only ever be one update key, right? You can't have 2 keys that are both update. That's not how tables work. So we're doing a proper set, right? So now that we've explained that, so what we can now do here, so num click set 0, that's just sort of like initializing our value. So now we can define a message equals you clicked dot num clicks get times, and then we do num clicks dot dependent set function. This might look a bit weird if you're not used to it, equals true. And this function is going to be our update function. And here we just update our message in response. And this still works, right? If we were to print message down here, it would say you clicked 5 times. If we were to print it up here, it'd say you clicked 0 times, right? So you can pause the video if you want to absorb all this so far. We are kind of going at breakneck speed because Fusion has lots of theory behind it. The implementation is actually relatively simple. Like you can understand the implementation on a technical level. Like we're not using anything crazy, like we're not using function environments or something, but yeah. So something to notice here is that we are duplicating this assignment twice. So what we're going to do is we're going to put it in an update function. So say message, I will do local function update. And then do that. So now we can just call update, and then we can replace this function here all with update. And now you can see this is starting to like look a bit more like a candidate for an object again, right? So especially what if we wanted to transform this message, right? So let's say we wanted local uppercase message. Perhaps we want this for stylistic purposes in our UI. We want all of our fonts to be in uppercase. So local function update uppercase message equals message upper, like that. And then we do update, and then what? Do we do num clicks again? I mean, Sure, technically we can do that, but we don't really depend on num clicks. We depend on message. The problem here is that message is now acting both as a sort of dependency of num clicks, but it's also now a dependent of uppercase message, right? So uppercase message uses message. So we essentially need to do the same thing all over again, right? So we can copy down our code for our value objects here, but instead of set, it's going to be update equals function. And we don't need to pass in a value here. Instead, we just say message self.value that equals you clicked num clicks get times, and then we go for our dependents and we update those. And finally, message.dependentSet. And you see here we kind of need to change how we're doing our dependent set. We will do, instead of just calling dependent like a function, we can do dependent update. And sorry, there you go. Num clicks dependent set message equal true. So hopefully you can see what we've done there. So message depends on num clicks. So num clicks dot dependent set message equals true. And whenever num clicks changes, we call update on our dependents. And in our case, update here will, update our value. We also need to do dependent update here. And what you might have noticed we've just built there is a rudimentary version of computed objects, right? Computed objects, well, they get updated and you can get their value. Yeah, so there we go. And uppercase message, we can now do the same thing. So uppercase message. Well, this is just going to be message get upper. And then message.dependent set uppercase message equals true. I guess something we also do need to technically do here is message update and uppercase message update. And that's just done just so we get like our initial values in there, just like we did num click set 0 up here. So at this point, it probably would be worth extracting these into constructor functions. So we'll say value, initial value here, or val, sure. And so we're just going to do self._value equals nil, and function self get return self._value, function self set new value self._value equals new value, and we'll just copy that up here. Basically, we're just moving this code into constructor function. Obviously, we need. We could actually just do this with local variables here because we're doing enclosure-based objects. We probably won't do this in Fusion for like performance reasons, but value equals nil, local. Well, actually, you don't even need to do value, so we just do value equals initial value, and that'd be fine. And local dependent set equals that. Though also that does mean we now need to have a way of adding dependent set stuff. So actually, we will just do that as private fields. Sure. Now we do self._dependent set. Yeah. Anyway, you get the idea. So this can now be replaced with value 0. This is now the same thing. And we will do the same thing for computed, except this is now going to be update. And here we're going to need to take in some function that will declare it will declare what the value should be. So we'll say this is callback. So self.value equals callback, like that, and return self. And of course we need to do this here. But the problem is obviously we need to depend on something, so we'll say dependent or a dependency would be the correct term for that. So a dependency dot dependent set equals that. And this kind of looks like a computed object. It's not quite the same. We're not doing proper dependency management yet. We will get to that. And obviously we need to update ourselves. Self value equals nil. And then we will do self update. Like that, and return self. So now we can do message equals computed, num clicks, function, return, you clicked, dot num clicks, get, dot times. And then uppercase message in a similar vein equals computed, and it depends on the message, and this is just going to be message get upper. And we can remove all of that, and we can move all of this. So we're starting to get towards Fusion's state objects, but we're obviously missing a very important piece of the puzzle, right? How on earth are we supposed to manage our dependencies? We can't just pass in just a single state object like this. What if we need to use two of them? So there's many different answers to how you do this. Roact's answer is joining bindings, which is essentially creating a computed object that just magically works. A blend solution to this is instead of passing in a single object here, you pass in an array of them, which works for simple cases, but it does not adequately model complicated relationships. Like, what if you only depend on something sometimes, right? What if the thing you're depending on dynamically changes? It's like you can't really model that. So what Fusion does is it actually automatically tries to figure it out for you. So let me explain sort of how this is going to work. So we can actually figure out when we are running inside of this function by using a secret variable, right? Before we implement this, we just need to define this up here. So we say local is running in computed equals false. And what we can do is just before we call the callback, we can set this variable to true. And then while we're in the callback, it'll be true. Then afterwards, we can set it to false. Right? So if we were to do print is running in computed here, this would print out true. If we were to do print is running in computed out here, this would be false. Right? So that's kind of interesting. We can change the state of our program specifically for when we're in computed callbacks. So what we're going to do is we're going to use this trick to actually do a bit of dependency management. What we're going to say here is local current computed equals nil. And we're going to say current computed equals self. And then we do current computed equals nil. So for all the duration that we're in a computed callback, we can read current computed to figure out what computed we're actually in. Now you might notice I've defined it all the way at the top of the file, and that's because the next trick is to do with the fact that whenever we access a state object, we call its get function. In other words, like whenever we use a value inside of our computed, we actually have the opportunity to run some code, specifically up here. So what we can say is if current computed, then something, right? Now the reason why this is useful is because if we're inside of a computed and we use a state object, we probably want to add that state object as a dependency. So what we can do is we can say, you know, self.dependent set on current computed is true, right? So the current computed that is using my value will depend on my value. That kind of makes sense. And so we can do that again like this. And suddenly, well, we don't need this down here. And we don't need this dependency argument or anything. We can get rid of this. And just like that, these computed objects will now correctly identify these dependencies here. Except I did kind of lie a bit to you there, because there is a small detail that is missing from this system. And that is that if these functions get run again, say if we update twice, we don't actually clear out our dependencies from before, right? So let me write some code that will exemplify this issue. Say, for example, we have local width equals value 25, local height equals value 50. We'll say local selector equals value false. We'll say local length equals computed function. And what we're going to do is, depending on the value of the selector, we will use either the width or the height. So say if selector get, then return width get, else return height get, end. So let's follow what exactly this is going to do. So starting from the top here with if selector get, well, we're calling get here. So we go up to value get. If we're in a computed, which we are, well, then this value has one dependent, which is the computed. So we are adding the computed as a dependent of the value. And so then let's say this is false, as it says above. So we go down to here and we say return height get. So height will add one dependent, which is the computed object. So the computed object is added as a dependent of the value object, right? So selector and height both have one dependent, which is length. So the problem comes now. Let's say we change selector to true. And well, when we do that, we say self.value equals new value, right? So the selector has now been set to true. And then for all of our dependents, in this case, which is length, we call its update function. And so obviously the update function sets current computed and it runs the callback. So if selector get, well, we are inside of a computed. So we add selector, or we add the current computed to the selector object as a dependent. I mean, it was already there, so we're just overwriting true with true. Pretty easy. And then height get, right, we do the same thing, and we or width get, sorry, because we actually did change, right? So selector is now true, so width get. So width is also going to receive computed as a dependency. Or a dependent, sorry. But what's the problem here? Well, we never got rid of height, right? Height is still in there. So if we were to take a look at height, length would still like be a dependent. We never got rid of it. This is sort of like we are adding dependents, but we're not removing them. So the solution to this is, unfortunately, we need to keep more information than just dependents. We also need to keep information going up the other way. We need to keep track of dependencies. So dependency set equals blah. We only need to do this for the computed because a value has no dependencies, right? Values don't depend on anything. They're just set by the user. Computeds, however, they depend on other objects, usually value objects, but it could be another computed object, for example. So what we have to do is we have to obviously maintain the two-way relationship. So current computed dot dependency set self equals true. Right? So computed is a dependent of the value, and the computed has one dependency, which is the value, right? Value is a dependency of computed. Computed is a dependent of the value. So it's just a two-way relationship. We do this down here as well. And also don't forget our underscores, really bad. And then what we can do is just before our update, we'll say for dependency in pairs self.dependency set, we will say dependency dot dependent set self equals nil, like that. So what we're doing here is we're going through all the things that we were depending on, and we're saying we are no longer dependent on your value. And then what we can do for ourselves is we say just table.clear self.dependency set, right? Because we no longer have any dependencies. We've just cleaned out our dependencies. That's what we've done there. And then those will obviously get repopulated by our callback. And so essentially we clear away all of our dependencies and then we re-add them as we go through our computed callback. And then by the end of it, we will have a new set of dependencies and our dependencies will have our computed objects as dependents. Nice and easy. So this all works now. And I mean, this is basically the bulk of what's going on here. But there is still something that we are missing here. I mean, we're going to be saying this a lot, right? I mean, there are lots of problems with the way that we've written this code. Mostly to do with stuff like error handling, which I'm not going to go into. Error handling is just like, if you want to learn more about error handling, just DM me about it or something, because it's really not interesting and it's not really relevant for understanding how Fusion works anyway. But yeah, so let me build you a neat little situation. So we have, for example, a number of coins, which is going to be a value of 100. I have, let's say, local item price equals value 25. This is like one of my go-to examples. So say local final price or final coins. Final coins equals computed. And in our computed, it will automatically put dependencies for us. It will return num coins get minus item price get, like that. And then we will do local message equals computed function return you currently have num coins get. Where's num clicks coming from? Weird. You currently have num coins get dot dot. And then do new line. After buying this, you will have dot dot final coins get. Now I've constructed this in a very specific way. Like obviously this is a realistic example. You would probably do something like this in your UI code. I'm sure you can imagine. But in order to understand this properly, we need to open paint.net and draw a diagram. One of my favorite things to do. So we'll just make it black background so it doesn't just blind you. And I'm going to draw some dots. So we have num coins and item price. And then we have final coins will go here. And then we have our message down here. And I'm just going to label them as such. Num coins, item price, final coins, and message. So final coins, yeah, it uses num coins. We'll just make that a bit bigger. It also uses item price, and the message uses num coins and it uses final coins. So what I want to draw your attention to is I want to draw your attention to this triangle here. You can see message depends on num coins directly, but it also depends on it indirectly. And this will cause a problem in our system. And this is a very subtle problem that nobody really thinks about. Especially like Blend doesn't consider it, I don't think. Roactive doesn't think about it. You know, lots of systems don't think about what this means. So let's walk through what exactly this will do. So let's move to red pen. Let's say, for example, num coins gets its value changed. So it's going to take a look at its dependents. It's going to say, oh, so message is a dependent, so update the message. And final coins is a dependent, so update final coins. Now final coins, it's going to take a look at its dependents and it's going to say, oh, message depends on us, so message needs to get updated. But notice what just happened here. We updated message twice. And the first time we did it, it was just nonsense, right? When we first updated message, we hadn't updated final coins yet. So it'd just be spitting out nonsense, right? It's inconsistent. So what we need to do is we need some way of num coins saying, okay, so message needs to be updated, but it still depends on something that hasn't been updated yet, so we're not going to update it. Instead, we're just going to update this first. And now we can update message because both the things that it uses have already been updated, so it's safe to update it. This is an important step because it means that your message function here, like the callback for your message update, whatever, will only get run once, and when it does get run, you are guaranteed that everything it uses has already been updated before it. Now, if you want to look this up on Wikipedia, this is actually known as topological sorting. So here's what you have to do. So the first thing we need to do is we need to mark like everything. So we're going to say we want to update num coins. The first thing we have to do is need to mark everything that num coins is going to update. So we can just do this easy. We'll just say message is going to be updated at some point, and final coins is going to be updated at some point, because those directly or indirectly depend on num coins, right? This is basically just a simple flood fill. Then what you do is you go to the dependencies of the dependence of num coins, and you say, okay, has final coins been updated yet? And has num coins been updated yet? If the answer to both of those is yes, then you update it. If the answer is no, then you don't. Something important to note here is that we are only considering marked values, right? So, for example, final coins is not going to say, oh, item price hasn't been updated yet, we're not going to update. Well, because item price isn't going to update, we haven't marked it. So item price is basically just ignored, right? So final coins here will be updated first because, I mean, num coins, obviously, like, num coins is where it began, and there's no other marked values that it uses that haven't been updated yet. So final coins is allowed to update. Message, however, is not allowed to update because final coins was marked and wasn't yet updated. So then, once we've updated final coins, we can then move on to message, and we turn around with message and we say, okay, so num coins, obviously that's where we started, so that's fine. And final coins, okay, yeah, it was marked for an update, but it has now updated, so message is now fine to update. And that's basically how topological updating works in Fusion, right? That's the formal name for it. So to recap that, just in case, right? So start off by marking everything that needs to be updated. So message needs to be updated and final coins needs to be updated. We are now only going to consider the marked things. So we start with final coins. It depends on num coins and item price. Item price hasn't been marked, so we ignore it. Num coins, I mean, obviously it's just kind of implicitly marked because that's where we started. So everything that's been marked has been updated, so we update it. We take a look at message, and okay, so message here, num coins has been marked and updated, final coins has been marked and updated, so it is safe. So let's now try and actively break this, right? So let's try and update message out of order. So we do num coins, and let's say we just so happen to go to message first. So we're going to go to message first, and we're going to mark it. And then, okay, so what else does num coins depend on? It depends on final coins, so we'll mark that as well. And then final coins, what's that depend on? It depends on message, or it's already marked, so it doesn't really do anything. All right, cool. So now we're going to do the updating. So we go down to message first. And so num coins, well, yeah, that's marked and updated because that's where we started from. Final coins is marked, but it hasn't been updated yet. So we do not update message yet, because if we were to try and update message, we would be using the old value of final coins. So now we go down to final coins instead because message didn't work out. Final coins, okay, so num coins is marked and updated. Item price isn't marked, so we don't care. So final coins is allowed to update. And then what does final coins have? Well, the arrow goes down to message here. So num coins has been marked and updated. Final coins has been marked and updated. Message is allowed to update. So with this system, message is always guaranteed to update once, and it's always guaranteed to update after everything that it uses. So let's implement this. So the first thing we're going to do is we're going to take out this stuff here, and we're going to create a new function for doing this. And this function, we're going to call it update all. And this will just update everything that the state object we pass it has dependence for, whatever. It updates all the dependencies, I guess. So it says, call it ancestor. And then what we can do here is that function will run the aforementioned process. And so we can just do that here. So when we do update all of the value object, you can imagine that's like update all like num coins. And well, actually, we don't even need it for the computed object because that's all done as part of the same process. Sorry, there we go. So let's now implement this. Now, it turns out there's already a really good implementation of this in Fusion. If we go into dependencies, update all. This is actually Fusion's version of the function. So we will basically be working on that. We'll say local marked, we'll call it. And now we need to do sort of a recursive algorithm to go down through all of these arrows to mark everything. Remember those downwards arrows, that's dependent, right? And if we go up the other way, it's dependencies. So we'll do, firstly for, say, okay, local function mark, we'll say mark dependence of object. So we're not concerned about efficiency here, so we'll just say marked, we'll say for dependent in object.dependent set. Well, that's not correct at all. We need to do pairs, and we need to have the underscore like that. Do marked dependent who's true, then mark the dependence of that dependent. So sort of recursively going all the way down the tree to mark everything out. So we will then mark the dependence of our ancestor. And oh yeah, actually it's probably be better to say that, right? Because that basically does the same thing, except it will also include the ancestor in the marking. So basically, after the end of this, marked will contain the state object. It will also contain all the computed objects that use the state object. It contains all the computed objects that use the computed objects that use the state objects, etc., etc., etc. Basically, just goes all the way down the tree, marking everything that's going to be included in our update sequence. So now here comes the second part of the process. We'll say local function update dependence of object. And here we're going to say, right, so the first thing we need to do here is we need to do that check, right? Are all of our dependencies, have they all been marked and updated? So we can say for dependency in pairs object dot dependency set do, well, it is really more like an update function, and this is more like a mark function. We'll just make this naming simpler. Like that, I guess. I don't know, it doesn't really matter, but yeah, so for all the dependencies, we'll say if not marked dependency, then continue. So basically, any dependency that has not been marked, we will ignore. So say otherwise, if not updated dependency, return. Right, so do not update this object if its dependencies have not been updated. So we'll say local updated equals blah, like that. Then we update the dependence. I mean, actually, really. Yeah, we'll refactor this a bit. We'll actually do this inside the for loop this time. And we'll say local all dependencies updated equals true. Otherwise, if it's that, then we'll say false and then break. So we'll say if all dependencies have updated, then we update dependent like that. So then to update the object, we'll just say if object.update is not nil, then object update like that. Easy peasy. And then we can just do update ancestor. And right there we have just implemented the same thing as this, except it uses recursion. So it's, for technical reasons, it's less good. There's stuff like stack overflows to consider, but this is basically what we're looking to do. So you can take a second to rewatch that section, absorb it. I know it's a lot, but basically this will do everything we need to do. Or at least it should do. I mean, I'm not going to be making an addendum for this video if anything's wrong, because it's more about the concept than it is about the code. So basically what we can do here, we say numCoins set to 25, and then that will set the value object here. So it sets the value object to 25, then it calls update all with value object. So that will just mark everything that depends on the value object, and then it will update everything that has been marked in order, basically. So it will mark it, and then it will update it only when everything else it uses has been updated. Nice. And, well, not nice and easy. It's actually, we are getting into more advanced stuff here. So Fusion, to my knowledge, is currently the only framework that actually does topological updating. But I put a very high premium on it because it lets you do some very cool stuff. So let's move on a bit to, what should we move on to? So yeah, let's move on to nested computed objects, because this is where stuff really starts getting interesting, and you'll sort of start seeing just where some of the complexity of Fusion comes from. So let's now do something a bit cheeky. We'll say local, let's say local button text equals value hey there. Now we'll say local button. We're going to actually create a button from the button text using our current technology. So we'll say local button, we'll say local b equals instance.new text button, b.text equals button text get, like that, return b. And so, of course, like this so far seems fine, except let's say we want to extend this button to have some state. Say, for example, we want it to have local is hovering equals value false. And then we'll just say, I don't know, local function update button color. And this will be b.background color 3 equals if is hovering get, then color 3.new 110, else color 3.new 111. And then we will do update button color like that. And what I've actually inadvertently done here is I have used a value object defined inside the computed, but I've used the get function on it while we're still in the computed callback where the thing was created. So this is going to lead to a very strange issue where if, for example, we did is hovering set true, the entire computed where this was created would rerun. That's a bit of a problem. So yeah, this is not fantastic. And in order to actually combat this, Fusion actually ends up having to maintain a stack of like, essentially it's like creation scopes, where basically if you create an object inside of a computed, it gets added to a table somewhere, and then this code here will not run if like the current like value object was created inside the computed, right, just using that table. We're not going to go into too much detail about that, but that's just one really important sort of self-referential case that if you were to create something like Fusion, you would need to handle. I can actually show you the specific way that we handle this. So this code here is done in use dependency. So you can see dependency set dependency equals true there. But you can see like here we are using a stack, and we are saying like if the dependency is within the table, then we do not add the dependency. So that's basically that's the interpretation of that code. I know it's very confusing and obscure, but that's just that's like a relatively important case that you do have to handle here. And of course, in order to declare that the object has been created, we also have another function, init dependency. So this is called by, for example, the value object when it's created, and it basically says it's like for all of the tables created by the computed objects to store like new objects in, we'll add ourselves into that. And so, I mean, yeah, this is very confusing stuff. I don't think I'm doing a very good job of explaining it. But all of that stuff to do with stacks and to do with like that sort of like inside stuff, that's basically just solving for the case of when you create a value object inside of a computed and then you use it. So that's an interesting little tangent. I mean, of course, I'll take a second to talk about error handling as well. If callback errors here, well, we're never going to reach this line of code where we set current computed equals to nil. And so you actually do have to run this in a pcall. So callback, But there is a slightly sort of mischievous little thing here that can happen. If this errors, then it's not going to have completely repopulated your dependencies, right? Because remember, we're depending on this callback to run to completion so that it can get all the state objects it needs, which will then add all the dependencies that you need. But because we cleaned out this table, this callback, if it errors, it's not going to finish collecting all of those state objects into the dependency set. So you're going to end up with a corrupt dependency set. That is a real problem as well, and Fusion has some special mitigations for that as well. It's pretty easy. You can just restore the dependencies that you had before. But that's just another thing you have to be cautious of, right? And so, yeah, I think we have covered most bases here. But there is something I do want to point out, which is a downside of this method, right? Say, for example, we have this function here. So local function, we'll say, I don't know, print text, return, or say print button text get end. And then inside of our computed here, we're just going to print the text for some debugging purposes or something. Then we'll just do return blah, blah, blah. And there's subtle behavior here, is that because this print text function is called inside the computed callback technically, this call to button text get is going to add button text as a dependency of this computed. Now, in this example, that seems like the thing you want, but actually this introduces a form of what's known as function coloring, where it's just like, where you call print text from will change how it behaves. Like if you just call print text out here, right, it's just going to print the button text and it's not going to do anything. If we call it in here, well, that's going to add a dependency to button. If we were to call it in another computed, it will add dependencies there. And this is generally a downside of this current system, is that it's really hard to predict whether this code here is going to add dependency somewhere or not, because you don't know where it's going to get called from. So that's another thing for your consideration. But anyway, let's now move on to observers, right? So observers is also known as compat in v0.1. I know, a fantastic name. But basically, what if we want to run some code whenever button text changes? Well, currently we'd have to do, local object equals, dependency set or whatever. Ooh. But like, nobody wants to do that, right? That's just long. We want to just be able to say like button text dot on change equals da da da. So what we're actually going to do here, we're going to use a generalized solution. We're going to create what's called an observer object. The reason why is because we don't want to do on change on both our value and our computed objects. We just want to have one on change event. So we'll just do, or one implementation of the on change event. So we'll do local function observer, and then we'll say watched, like that. And we can just copy and decode from computed here, just to get a nice baseline. So then self update, we're not going to call that right away, because all we're going to be doing when we are updated is we'll just say on change callback. We'll say on change callback, like that. And then get obviously stays the same. And then our dependency set here, well, is going to be watched equals true, because we have a dependency on watched. Similarly, we're going to have to say watched dot dependent set self equals true. So it maintains the two-way relationship. Remember, that's important. And what this will let us do is it just lets us say local observer equals observer button text function, and print the button text is now button text get, right? And what this does is it basically watches button text changes, and then when button text changes, it runs the function. But internally what it's doing is it's essentially creating another object as part of our reactive graph that we've constructed here. And it's adding it as a dependent of whatever thing you're watching, and whatever thing you're watching gets that dependency as well, blah, blah, blah. And basically what will happen is update all up here when this gets called by sort of like something in the chain. It goes down through the computed objects, down, down, down. Eventually it sees your observer, and then, it will then update that. Well, this code here, currently it does assume that our observer could have further dependents, but obviously we don't have any and probably never will, because our observer doesn't really, or shouldn't really be providing values, right? There you go. So there we go, right? Observer, we have our computed, and we have our value. We now have basically got the infrastructure of Fusion here. We can actually start writing Fusion code, basically. I mean, of course, there is a subtlety here in that the actual observer object in Fusion, if we go take a look at it, on change is actually like a method you can call rather than something you pass in the constructor, which is mainly just done for forward compatibility. Like if we wanted to add another event to observer other than on change, we have the ability to do that. For example, if you wanted to add on bind or something. So yeah, anyway. So, with all of this in mind, it's now time to start taking a look at how Fusion does instances, right? Because we've done dependency management, we've done topological updating, we've done all the state objects. This is like the bulk of Fusion. So let's take a look at how to make instances. So obviously we'd say like, I don't know, local button equals instance.new text button. And we'll say button.text equals button text get. Now we do, oh, we have this observer here. So we'll just do observer button text get, and then button text equals button text get, like that. And I mean, let's be real here. This is kind of slow and clunky. What we really want to do is we just want to be able to specify the text button with all of its properties. We want to have a nice like API for it, because this is going to get long and boring after a while, even if it is technically correct. So Fusion introduces a utility for that called new. We give it class name, and Fusion actually does a little trick here where it does return function properties like that. And the reason why is because it lets you do like new text button and then like that. Obviously, because it's a function returning from a function, so we call new text button, that returns a function, then we immediately call that function with the properties. But Lua actually has some syntax sugar here, where say you have local function, well, we have print, right? So if you do like print foo, or if you do print and then like, I don't know, a equals true, some kind of table, right? If you have a function call that just passes in a single string literal, so a single sort of written out string, you actually don't need the brackets. Similarly, if you are just like writing out a table and it's your only argument, then you can do that too. Which means down here where we have a function call that just takes in a string like that, function call that just takes in a table like that, and oh, would you look at that? That's where Fusion's really nice syntax comes from. So yes, that is actually valid Lua. This is not special pre-processing. It's just two functions inside of each other and a little bit of sleight of hand. So what we can do here is we say local instance equals instance.new class name for prop name, prop value, in pairs properties, do instance prop name equals prop value, and return instance. Now this code should be very familiar to anyone who's ever used rbxutility.create, because our new function here is basically rbxutility.create. So let's try and use it, right? So we just say new text button. Now I always say like parent equals game get service players dot local player dot player GUI dot screen GUI, I guess. Let's just pretend that exists. And text equals button text get, like that. And then so we've created our instance, and we then set up an observer on it, which will update the instance as button text changes. But we're going to be doing that a lot, right? Like our UI typically depends on lots of changing values, so it'd be quite nice if we could just pass in button text and have the observer set up for us. So that's exactly what we're going to do. So in order for this to work, we are firstly going to need to go up to a value here. We're just going to need to say like self.type equals state. So say this is like a state object. Computed is also a state object. Observer is technically a state object, I guess, but it's kind of a bit of a clunky thing because it doesn't actually provide a value. You could probably break Fusion by doing that. So what we're going to say here is we're going to say if type of prop value is a table and prop value.type is state, that means we've passed in a state object. Otherwise, it just means it's a regular property, most likely. So here we can say instance prop name equals prop value get, and then we can do our observer thing, observer prop value, and then we just copy this in here, like so. And that means we don't have to do it down here, and that means that our button code has now become a lot simpler. So let's move this up here with everything else that we've already implemented. You can see, right, that this is not a lot of code to already get to something that's very Fusion-like. So that's pretty cool. So what we now need to do is we need to do, firstly, we need to move parent to the end, right? Because currently we're not doing any special handling of parent. So we'll put some comments here. So we'll say state object. So say this is just regular property. We'll say if prop name is parent, then continue. So just don't set parent. And then we'll just do instance.parent equals properties.parent. Just like that. That'll make sure that parent gets set last. And yeah, so that's good. Obviously, the next thing we want to do is we want to be able to add children. So how do we do that? Well, the way that Fusion chooses to do it is it chooses to use a special key, it's called. So if we define local children, it'd be like this. And we'll say children equals blah, and it'll just be like new UI corner with like a corner radius. And this be like 0,4. So what our new function can do, like we could check if the property is the children key. But something else I would like to do is I would like to move the functionality into children. And so this is what the actual Fusion implementation does, right? If we take a look at here, so for key value in pairs props, right? So if keys type is string, and if the key is not parent, then like we bind the property, which is just what we just did. Otherwise, if it's a special key, so something like children, then it will add it to an array of special keys up here. And then it goes through like all the different parts of that array and it applies them. So we're not going to do that. Instead, what we're going to do, we're just going to go for the simpler hard coding thing. This is what you will see if you use Fusion version 0.1. So up here, we're going to say if type of prop name is a table, and I mean, actually, we can do this simpler. We just say if prop name is children. Oh, prop name is children. Then this is assigning children. Then we just continue off to the end of it, so we skip everything else. So I mean, we could just put it in the else if, actually, like that. It's a bit clearer. So prop value is probably going to contain some children. So for now, we'll just keep it simple. Right, we'll just say for underscore child in ipairs prop value, do child.parent equals instance, and right, we are missing out a lot of like subtleties here, but hopefully you get the idea of how Fusion does that sort of stuff. You can imagine on event and on change behaving the same way. Right, it's going to be like you can just check for that and then you can do that the specific thing. This is the basics of how the new function actually works. Right? And so we are now sort of getting to the point where we have a sort of complete model of a really basic toy Fusion. Beyond this point, it's not really useful to continue building on this because we're just going to end up writing a lot of code to handle lots of very specific things. So what I'm now going to do is I'm actually going to jump over to the actual Fusion code, like the actual Fusion code base. I mean, we can come back here like from time to time just to like check up on like things. But what we're going to do is just close. Oh, we have a button to do this. What am I doing? All right, so this is going to be the source code of Fusion. So should I save it? We'll just put it over here and let's see. take a look at init.lua. Right, so this is Fusion's sort of like main module here. So first thing we're going to take a look at is we're going to take a look at the actual new function here. So let's take a look at it. This is what new looks like in Fusion. It looks substantially simpler than what we just wrote, which is because we are doing a bit of deceitfulness by actually doing all the property applying somewhere else. So you can see, obviously, we put a pcall around instance.new just in case you try and create something you're not supposed to. Then we apply our default properties. Those are stored in default props. As you can see, this file here is just a bunch of default properties. And then we call this thing called apply instance props with something called a semi-weak ref. Right. So this is probably going to be the most difficult to understand part of the video, is semi-weak refs. What are they, and why does Fusion use them? And this is where we start getting into garbage collection. And if any of you guys have followed me on Twitter for the past 6 months, or even longer actually, past year, oh boy, I've talked a lot about garbage collection. It's very difficult. I mean, technologically it's very simple. So we'll take a look at what semi-weak ref does first. So this is all about weak and strong references to instances. The idea behind semi-weak ref is basically that if you have a semi-weak ref, it is a table, of course with type semi-weak ref, that just has an instance property set to whatever you give it, right? So whenever you have a semi-weak ref, it's basically just an instance in a table. At first you might think, well, what's the big hold up here? Well, the specific problems come with how that table behaves, right? So, like, if your instance is accessible from the data model, then the table will hold the instance in memory. However, if the instance is not in the data model, so if it's not accessible from the data model, say it's like in nil, then this table will not hold the instance in memory. It will, like, if you lose the instance in your own code, then the instance will just evaporate into thin air, and this instance property becomes nil by magic of Lua's garbage collection. The reason why we need this behavior is because Roblox does references for instances pretty wrong, right? And like, it's really hard to describe. But essentially, what semi-weak ref allows you to do is it allows you to access an instance at a later time, but it won't hold the instance in memory if it's the only thing in your code base that is holding the instance in memory, right? So it's basically done so that Fusion will not just cause memory leaks. So like, now, let me just illustrate this with an example. This is really, really difficult to explain because this is really getting into the grit of like Lua. So let's say, for example, local part equals workspace.part. Say there's a part in the workspace. Right? And let's say, I don't know, part equals nil. Then we will wait for 100 seconds and we will set part back to workspace.part. So let's walk through what this code does. So when we first run this code, Roblox sees that you're trying to access workspace.part. It will create a Lua object to represent that instance and it will assign it into the part variable. So the part variable contains a reference to an instance object representing workspace.part. So then on the next line, we set it to nil. So Roblox is just like, okay, so nobody is using that instance object anymore in your code. So that instance object is going to get destroyed. It's going to get cleaned up for garbage collection, right? So this basically means the instance object in Lua no longer exists to represent workspace.part. Then later on, when we run that same line of code, Roblox will create another new instance object on the Lua side of things to represent workspace.part, and it assigns it to the variable. The sticking point here is that this instance object and this instance object are not the same thing, even though the instance was always accessible, right? The way that this should work is that as long as workspace.part is in the workspace, and there is at least some like weak reference to it in Lua, the instance objects here and here should be the same, right? Or at least like they should have like this. They should be the same basically, because if you're referring to the same instance, then you should be referring to the same instance object. It would make sense. But in Roblox, this is not the case. You can actually have multiple instance objects on the Lua side referred to the same instance object, leading to some very, very weird and not very useful garbage collection behavior. It means that, say for example, you have like local table equals workspace.part equals true, and it's like then you say, I don't know, say set metatable table mode equals k, right? And they'll say later on here, we'll say wait 100 seconds. I will do print table workspace.part. This will likely print nil. And I'm just going to explain to you why, because that probably seems very weird to you. So what this code is doing here, so we create a table where the key is workspace.part and the value is true. Easy enough. This line is where most people are going to have trouble because most people don't understand metatables. But what this is basically saying is that, like, it's saying that if our code is the last thing using workspace.part here, if our table is the last thing using workspace.part, it's okay to just automatically get rid of this from the table and just like clean it up from memory. So this is typically done because, say for example, you destroy workspace.part and it gets removed from the game. You don't want this table to keep workspace.part around in memory, even though it's already been destroyed and removed from your game. So you basically allow Lua to just automatically remove workspace.part from your table if your table is the only thing still keeping it around. That's basically the simplest way I can describe that line of code. So if we just wait 100 seconds, this is basically a long time, basically just an arbitrary amount of time. Later on, when we go to try and find workspace.part in our table, it will return nil because the actual instance object that Roblox created to represent workspace.part, well, it wasn't held in memory, right? The only place in Lua where that instance object was used was in this table. And because our table allows that instance object to be cleaned up, it will be cleaned up because nobody else is using it. So when we come down here, when we're actually indexing workspace.part here, we're actually indexing using a different object, even though it's the same instance in the data model. If you think that's really weird and bizarre and a really dumb design decision on Roblox's part, you're correct, because this is a very dumb decision for consistency reasons, right? I mean, the actual reason they did this is because of performance. But even then, this is like making the addition operator fail sometimes for certain kinds of objects just because of performance. It's an inconsistency in the language design. And it's not a very good one. And Fusion especially gets hit hard by this, because Fusion deals a lot with references to instances. Semi-weak ref is an attempt to fix this. Basically, what semi-weak ref does is it says, do mode equals k if workspace.part isn't in the game anymore. If it's like in nil, then it's okay to do that because you're not going to be able to access it with like workspace.part, right? It's considered inaccessible. However, if workspace.part is still in the workspace, we can obviously get back to it later. So we shouldn't allow this to happen, right? Workspace.part should not be cleaned up from Lua, which means that basically if table was a semi-weak ref, then this code would work. It would return true, right? So this is basically semi-weak ref is Fusion working around a horrible deficiency of Luau, which there's no good reason for it to exist. Fixing it would not be a breaking change. And, like, in general, it's just so dumb that we have to work around this. And, yeah, that's basically all this code does. It's just fixing Roblox's problems. It's just like, I mean, I don't know. Maybe the performance impact of fixing this actually is a bit of a problem. I don't know. I don't work on Luau. But personally, I think that if this is just for like a small performance gain or just the benefit of not maintaining some extra data structure in memory, like, it's not worth it for this horrible behavior. It's like, this sort of stuff is the reason why Roblox games have memory leaks left, right, and center, is because you can't depend on mode equals k for instances. It's just like, it's just one of many very confusing garbage collection decisions that Roblox have made. Anyway, so we'll close that and get out of that. So that basically, semi-weak ref is just, it's basically wrapping up instance references in containers that behave better with garbage collection. So if we head back to the new function, how long did I spend ranting about that? Like 10 minutes or something? So yeah, so apply instance props, get props, and then just a wrapped up instance reference. Okay, so we go to apply instance props here, and you immediately see a bunch of functions. We can ignore those safely for now. We'll get to those in a second. So if our wrapped instance reference is already nil, then that probably means there's a problem somewhere. So we just warn for that because that's a good thing to do. And then we set up some tables, special keys, and cleanup tasks. So the purpose of special keys, this will store all of the special keys inside of your property table, like as we read them. And the specific 4 things here, these are different stages of initialization. We'll talk about that a bit more in a second, because every single special key can declare its own stage where it should run. So then we go through the entire property table, and we get the type of key using this function xTypeOf, and that's defined here, pretty simple. Basically, if type string is a table, so if x is a table and x has a type string, we return the type string. Otherwise, we just return type of x. Right. So if we go back to apply instance props. So basically, if the key type is a string, so if it's just a regular property and it's not parent, then we call this function bind property. And what bind property does here, it just says, okay, if the type of our value, if it's a state object, then we will set the property. So do instance property equals value get false. We just define that in this function here, so we can like p call it. So this is basically just like a safe property setting thing. And that's also what this is used for as well. And this function here, this is all part of set property. And then what we do is here you can see we create an observer on the value, and we say when it gets changed, update later. Now update later is defined here. This is a function that will set the property on the instance to value get false, but it will do it inside of a task.defer. Right, and this is called deferred updating. And this is a thing in Fusion where when you change a state object that you've passed into an instance's property, right, the actual instance property does not update until the next resumption cycle, or the next like render step, or the next whatever you want to call it, right? Basically, the reason why this is done is because value objects might get changed multiple times within the frame. And all we want to do, we just want to use like the result of that, right? So we just want to use like the latest value rather than all of the intermediary values. So we do this deferred updating thing. And so we just use will update as a way to just not do task.defer twice. You'll notice we're adding this to a table of cleanup tasks. This is this table right here. The reason why we do that is because when the instance gets destroyed, we want to make sure that our observer gets cleaned up. So we'll just run through the cleanup tasks and we will clean up everything that gets passed in. In this case, obviously, you know, in Fusion, like the onChange function on observer, it returns a disconnection function. So we're just adding disconnect function to our cleanup tasks. So the observer will disconnect when the instance is destroyed. So otherwise, value is a constant, assign once only. So this is basically, if we haven't passed in a state object, we can just do set property like that. Nice and easy. So that's that little bit of code there. I make things sound so complicated, I think. But anyway, so otherwise, if the key type is special key, so if this is something like children or on event or on change, ref, out, cleanup, whatever it is. Firstly, we get the stage from inside the key. So the actual keys here, like if you take a look at, for example, like out, you see this is actually, this is a table has type special key, kind out, stage equals observer, right? So that's just an example run. So we get the stage out from the key, and then we get the specific array out of special keys here, or it's really a set, I guess. So if keys equals nil, then log error unrecognized property stage. Basically, if your special key does not have a stage value equal to one of these, it will error. That's basically like an internal error. Otherwise, we add the key to this table with the value, right? So we save it for later. So otherwise, if it's not a string and it's not a special key, then we don't know what it is, so we error. Okay, so now that we've done that, now this is where we apply our special keys. So for every single special key with stage of self, we call its apply method. So I'm trying to think, are there any keys that do that? There's not children, cleanup is observer, on change is observer, on event is observer, out is observer, ref is also observer. Right, so there's no keys currently in Fusion that actually use this. This is not done currently. But this is basically anything that operates on the instance itself and doesn't need to know about any children or parents or something gets run first. Then any special keys to do with descendants, those are run, so they apply their stuff. So this is typically children, right? Children has a stage of descendants. So children's apply function gets called, and this is basically, this code here is what parents all of your children to your instance. It might look like a lot of code just to do some parenting, but we'll go through that in a bit. It is all quite useful. So then we'll say, if there is a parent defined, then we will bind the parent, just the same as we bind a regular property. So this is done basically later because you want to set all your properties and assign all your children first before you set parent, because once you set parent, that has to like connect a bunch of events and stuff, and like has to fire off a bunch of like ancestry events and whatnot, so it gets slower. So once you've set the parent, we can run any special keys at the ancestor stage, so any keys that depend on having the ancestor defined. Then finally, we run all the observer keys last. So these are just special keys that they're basically just watching the instance. So stuff like on event. Like on event is like observing the instance, or like ref is observing the instance, right? It's not actually setting anything up on it directly. It's just responding to changes or just responding to the instance existing, that sort of thing. Then finally, on destroy takes in our instance that's wrapped up in semi-weak ref. It takes in a cleanup function. In this case, it's just Fusion's internal cleanup function, like this. And it then takes cleanup tasks as an array. So basically, the onDestroy function, take a look here. This is like a custom implementation of instance.destroyed that properly works with garbage collection. So we take in our instance reference, we have a callback, and then we have a bunch of arguments to pass the callback. So whenever instance gets destroyed or it gets garbage collected by Roblox, we run the callback with the arguments. Pretty simple stuff, right? So you don't need to worry too much about this implementation, other than the fact that this is the most up-to-date battle-tested version of a proper destroyed event that I think exists on Roblox right now. So yeah. So this is basically saying, once our instance gets destroyed, call cleanup on this table of cleanup tasks. Taking a look at the actual cleanup code here, This right here is basically the functional version, or the procedural version, I guess, of maids, if you know what maids are in Lua. So you could just give it a task and it will destroy it. So if you give cleanup an instance, the instance gets destroyed. If you give cleanup an event connection, it disconnects it. If you give cleanup a function, it runs it. If you give it a table, then if the table has a destroy method, it calls it. Same for the other capitalization. Otherwise, if the table you've given it is an array, then it actually goes through all the things in the array and it cleans all of those up. Right? And this simple definition of cleanup is really all that you need to implement maids, right? Because if you wanted to implement a maid, like you say local maid equals blah, to insert something into the maid is just like, just do maid, say table.insert maid instance.new part, I guess. Or you could do table.insert maid function print. This will run on destroy. And like that. Then when you want to clean up your maid, oh, actually, you could even like, you do like, I don't know, function maid destroy if you wanted to. No, actually, we'll keep it simple. We'll just say clean up maid, and that will destroy your maid, right? That cleans up everything inside of it. Because maid is an array, and in that array has all your tasks. Clean up maid, easy peasy, right? Maids are a coding convention, not an object. I think Anna Minus separately came to this realization, but luckily I'd already released Fusion by then, so this idea was already out in open source, so I can technically claim I did it first. Yes! But it's not competition, it's just good coding practices. Yeah. So yeah, that's the entirety of new. Congratulations, you made it. But obviously, now you might think, okay, so we've gone over Fusion's entire new function, but we haven't actually gone over all the special keys yet. So we'll start with the simple ones. Right, so the cleanup key. Right, so this is obviously a special key. It's specifically the cleanup key. It runs at the observer stage, so this runs after the instance has been completely set up. And then the apply function here, it takes in whatever you've passed to the cleanup key, and it just inserts it into the cleanup tasks so that it gets run on destroy. Ta-da! That's how simple Fusion's cleanup key is. And then you have on event. So the way that this works is, on event is not actually a special key itself, it's actually a function. So you might remember that, oh, so button equals new text button, like that. And it's just like on event activated equals function, blah, blah, blah. What your code actually here is doing, this is actually a function call. Remember that it's like, when you have a function call like this in Lua, you can get rid of the parentheses. Yeah, so this is, on event is actually a function. You call it with activated and it returns a special key. Right? So that's pretty neat. Right? So the key is obviously a special key type on event, stage observer. And when you apply it, it firstly gets the instance reference from here. And then checks that it sort of checks the property on the instance. So it does get property on the instance for whatever event it is. So it says if that causes an error, or if the thing that's returned is not an event, then we say you can't connect to that event. Otherwise, if your callback is not a function, then invalid event handler. Otherwise, we insert into cleanup tasks the event connection, right? So just do event connect callback. And then the event connection returned by that gets added as a cleanup task so that when the instance is destroyed, your event connection gets cleaned up. Nice and simple. On change, much of the same story, except it's a little bit more complicated here because we don't directly have a callback. We actually have to write our own thing here. But yeah, and of course it uses get property change signal, so that's slightly different too. But yeah, so that's on event and on change. It's pretty simple to understand. Out, so this is a relatively new one. This is version 0.2. This lets you sort of set a value object equal to a property and keep it up to date. So this is obviously just Like we get the instance, get a change event. So say if the property provided isn't valid, then the error. Otherwise, if the thing that you have provided is not a value object, then we error. That's not a valid object. So if all that's good though, then we set your value object equal to the value of the property. Then we connect to that property change event, and we say if apply to ref instance is nil. So if your instance still exists, then we set your value object equal to the updated property value. So obviously that's added to cleanup tasks, so that when your instance gets destroyed, that property change event gets disconnected. And something else we do when your instance gets destroyed, we set your value object to nil because the property no longer exists, technically. So that's just a neat little thing. And we have ref, which is a bit simpler. So if the thing you provide is not a value object, then it errors. That's not a valid value object. Otherwise, it will set it equal to the instance reference. And then when the instance gets destroyed, it sets it to nil. So kind of similar stuff. And those are actually all of the special keys that Fusion implements right now. So you can go back and rewatch any of the ones that were a bit difficult to understand. But yeah, so we have now gone through everything except children, actually. So just before that, hydrate is very simple. It's like new, except it has less stuff in it because you're just providing the instance directly. We don't have to do any special processing. But yeah, so children. So I did almost forget about this one, so good thing I didn't do that. We're going to ignore the auto-naming stuff. That might happen in the future, it might not, we'll see. That's just an experiment. So I'll actually go through and I'll remove that all now. Like that. Right, and that should be everything. Right, cool. So let's explain how children works. So children is obviously a special key. It runs at the descendants stage, so it's concerned with obviously the descendants of the instance. So there you go, right? So by the way, the reason why Fusion divides its properties into these stages here is because when you're parenting children in to the instance, imagine they have like an ancestry changed event, right? Like we want that ancestry changed event to fire when the instance has finished having all of its properties set up, so that when the children see that event, they will see like the completely sort of populated instance, right? So the name will be what you expect it to, the background color will be what you expect it to, etc., etc., etc. So that's why that's done. So there is this update children function, and what this function does is it'll take a look at the children that you've given it. So it'll go through like all the arrays and state objects, whatever you provide as children, and it will parent in everything that needs to be parented in, and it will unparent everything that no longer should be parented. So it basically just updates the children, as the function name says. So we'll just skip over that implementation for now, because what's down here is important. So we have this function here called queueUpdate. It basically says if we haven't already queued an update, then like on the next resumption cycle or the next render step, we will update our children. This is deferred property updating, but for children. So it's the same thing. Obviously, when your instance gets destroyed, we set the children property to nil, and then we call update children, which because it's nil, it will unparent everything. Or will it? It should do. I actually think that will cause an error, but oh well. I'll patch that up in the repo. But yeah. So I think prop value should actually just be an empty array. So it's like children equals you have no children. Yeah. So perform initial child parenting. So we call update children once, and this will just parent in everything initially. All right, this is the first update. So remember that queue update, when we call queue update, it will call update children on the next render step. All right. So when we update our children, there is no longer going to be an update queued. Here we're just doing a bit of table flipping so that we have new parented and new disconnects as empty tables. Old parented and old disconnects are just going to be the old versions of these two tables from the last run. That's what that does, if you were wondering. So here we have this function called process child. And what this will do is whatever you give it, it will parent it into the instance. So if you give process child an instance, well, then it will say the child has been parented, adds it to the table. So it's just say, if it wasn't previously parented, so if it wasn't previously present, then child.parent equals blah. It doesn't apply parent twice if it doesn't have to. It's just like, otherwise, if it was previously there, we take it out of the old table. And the reason why is because at the end of this all, we're going to be going through all of the old things we've parented, and we'll be unparenting those if they no longer belong. This is basically just saying, okay, we've accounted for this, we can take it out of the old table, we don't need to process it anymore. So it's all like moving the child forward from the old table to the new table. So otherwise, if the thing that you're processing is a state object, well, then we get the value of the state object, and if it's not nil, then we process whatever's inside the object. And then we need to add an observer, which will watch the state object to see when the state object changes. So when it changes, we have to queue an update, right? So we, like, if you change what's inside of the state object, then the children might have changed, and therefore we recall process child. That returns a disconnect function, and what this does here, right? We're either getting, so if we already, like, if this state object was already previously present and we already created this observer before, it's going to exist in this table. Otherwise, if it's nil, then we create it here. So, but if it was previously here, again, we do the same moving forward thing. So sort of like move the observer from the old table to the new table. Otherwise, we create it if it wasn't there before. And then we just make sure that our observer is in the new table here. Just a little bit of notational trickery. So otherwise, if we've passed in a table, then we go through everything in the table and we process it. Every individual sub-child, right? So otherwise, if we pass something to children that is not an instance, a state object, or a table, then we log a warning saying, we don't know what you've just tried to parent. You probably shouldn't do that. And then, so at the end here, say, like, this is outside the process child function. We'll say, so if our property value is not nil, oh wait, so that actually won't cause an issue. So yeah, if prop value is not nil, then we process all our children. So say prop value is set to nil on cleanup, so we don't process children in that case. Right, that's fair. So basically that's just calling process child on whatever you pass into the children key. So what this will do is this will fill up new parented and new disconnects with all of the new instances and all the new disconnect functions that we created, as well as any instances or disconnect functions that we're bringing forward from before, which will leave old parented and old disconnects to contain all the instances that no longer should be parented and all the disconnect functions which sort of like come from state objects that are no longer present, or observers that are no longer present. So that's what we do here. We go through old parented and we get rid of them. We go through old disconnects and we disconnect them. That's the entire children key. It's a bit involved, but if you know what you're looking for, you should be able to find it in there. It is only 127 lines. So that's that. Finally, also I just realized I probably still have OBS on 1080p. Oops, I'm sorry. I will change that to 1440p for next time, but I'm currently 1 hour and 40 minutes into this session. So you're just going to have to live with 1080p. I'm sorry. I'm not restarting from the beginning. So that's basically all of Fusion's instance APIs explained. Congratulations. I guess it's worth taking a look at Fusion's state objects as well, even though we did already kind of finish up on them. So the value object, right? So when you create a value object, you just create your type is state, kind is value, got your dependent set, as we mentioned before. And obviously you have your value. This is all done with class meta tables, so we can have our methods up here. Basically standard Lua object. And then init dependency, this is declaring to the dependency manager that this value object was just created. So if we're inside of a computed and we use this value object inside that same computed, don't add it as a dependency because it doesn't make sense. So yeah, we talked about that before. Then we just return the value. And then the get function on a value. So there is a secret as dependency parameter. Don't use this. We're removing this next version. This is undocumented for a reason. Yeah, so basically we tell the dependency manager, hey, somebody just used us. So if you're inside a computed, you should add us as a dependency. And then it just returns its own value. Pretty easy. And then set here. So if our current value is the same as the new value, then we return early because nothing's changed. Unless you provide force equals true. This again, that we want to change this next version as well. But this is documented because it is quite useful. But yeah, so self.value equals new value. Then update all. We already went over the update all function. So that just updates everything that uses this value object directly or indirectly. And then we have computed. And so this here, similarly, we create an object here, same dealio. We have dependency set and dependent set, and a couple of other things. We also store the callback. Then we init dependencies, basically tell the dependency manager we just been created, same thing as before. Then we also update ourselves to get our initial value. So this here, so this first thing we do, we remove the object from our dependencies, and then we clear our dependency set. Something else we do here though, we actually maintain the old dependency set. So that will just store all the things that we were previously storing, whereas the actual dependency set is now going to be cleared out. So then we call this function called capture dependencies with our dependency set and with our computed callback. So what capture dependencies does is it basically does the thing we did before with the sort of set a global variable, then run the callback, then reset the global variable, and then return whatever the callback returned. Right? So it's just sort of it saves this dependency set to some global variable somewhere, so that whenever you call use dependency, whenever you call get, right, it will automatically add it will add the object to the dependency set, which is how Fusion does its automatic dependency management. We can take a look at that now. So this here, so say the previous dependency set, so if we were inside of something else, then we save it here. So we set the new global variable dependency set equals the set that we passed in here. And we set up some stacks here, which is all to do with making sure that if you create a state object inside of a computed or something, and then you use that state object inside the same computed, the computed won't get a dependency on the objects that was created inside of it. Right, so we went over that before. Then here we do xp call. So this is basically pcall, except we're using Fusion's error handler. And then once we've finished running the callback, we just reset the global variable to what it was before, and we get rid of the thing on top of the stack that we added. And then we just return whether it succeeded and the value that was returned, if any. That's basically how that works. And obviously shared state, this is, well, shared state. Enough said. Yes, these are just the global variables that we were talking about. And so that's, yeah, basically if using the entire dependency manager. So use dependency here. So just like if we currently have a dependency set that we need to save to, then check that the thing that we're trying to add as a dependency was not created inside of ourselves. And if everything's cool, then we just add our dependency to the dependency set. And init dependency here, so just say, okay, so get the current stack, the current thing on top of the stack, the current table on top of the stack. And then just like for everything in the stack, we just add ourselves as like, yeah, as created. I don't know if that made any sense, but basically this is basically just registering the dependencies as being created inside the current computed, so that if someone also tries to use it in the same context, it won't add the dependency. Yeah, that is a really, really difficult concept to explain. I'm very sorry if you don't understand that, but I can't think of any better way to explain it with my mouth. So yeah. We've gone through most of everything. We've gone through like cleanup and X-type of. I mean, restrict read. This is just standard stuff. Basically means that if you try and access something inside of like the main Fusion table that doesn't exist, it will just give you an error saying, hey, that doesn't exist. I mean, the only things we haven't really gone over is computed pairs, tweens, and springs. I don't want to go over computed pairs because we are replacing this. And we do already have a good article about that on ltop.github.io/fusion. So if we take a look at the Fusion documentation, go to tutorials, further basics, and arrays and lists. We are again also going to be updating the documentation very soon, so this will be like moved a bit. But yeah, this here just explains how computed pairs just works. If you want to actually take a look at the implementation of computed pairs, it's a lot of stuff. There is a lot of stuff here. So it's 222 lines. That's kind of massive for Fusion. So this update function is chunky as hell. But yeah, but basically all of this does is it basically just is. It's just the syntactical equivalent of like having an array full of computed objects, like, and you just create that array dynamically based on the contents of another table. But yeah, the article here basically goes into all the detail you will ever need to know about how this thing works. Because like the only thing really of note here is that computed pairs does have to sort of keep track of the values of its dependencies and compare them in order to see whether a specific key has sort of had a change in its dependencies in order to recalculate it. And this is done here with like should recalculate, right? So basically the reason why this is because update does not receive any information about what specifically has updated, right? Like, I mean, we probably could do that, and maybe I'll look into doing it in the future to make this code simpler. But basically right now, computed pairs has to figure out which of its dependencies have changed, and then it has to compare those against the dependencies of each thing in the computed pairs table in order to see, okay, does this specific key value pair need recalculating? And if it does, then it will recalculate it, which is all done here. And save dependency values, add to main dependency set, blah, blah, blah. And just find keys that are removed and then remove them. It's like, Like, the code is a lot more convoluted than the concept. But it's just a lot. We really need to tidy this. So yeah. Shall we move on to the animation primitives? Right, so we're going to start off with the color thing, because this contains something called OakLab. You might have seen this and been like, what the hell is this? Well, I'll show you what it is if we take a look here. So this is Bjorn Otterson, probably Icelandic, and I haven't actually looked that up, but he says, a perceptual color space for image processing. This article here introduces something called the OakLab color space. And basically, this is just like, this entire blog post is just setting out a different approach to color compared to RGB. And the idea of OakLab is that you get really nice gradients. Because I think we just Google OakLab, an interactive review of OakLab. Take a look here. So this is sRGB at the top. You can see the gradient. Now, as you interpolate between blue and yellow, you sort of pass through grey in the middle. That's not how actual colors work. And so sRGB is, you can think of it, it's not actually a color space. I mean, RGB is the color space, but like sRGB is a specific like profile of that color space. Color is complicated, but basically sRGB is what Roblox uses by default. This is how Roblox interpolates colors by default. And then these are other color spaces within which you can interpolate colors. So if you convert a color from RGB to CLAB format, then you interpolate those and you convert it back to RGB. You get this sort of gradient, which looks quite pleasant, but it goes through purple, which is a bit weird. IPT is another one. It goes for a nice pleasant green. OakLab, which is what Fusion uses. If you convert a color to OakLab format, then you interpolate it and then you convert it back to RGB. You get this really pleasing neutral gradient. It looks very smooth perceptually. Then that, which is, I believe that's the HDR color space that everyone uses. It has a similar nice gradient. There's some nice things with blacks and whites, with blues, red and blue, right? You can see OakLab has a really nice gradient here. CLab just really likes purple. And red-green, you can see here, like OakLab goes through like yellow, whereas sRGB does not. So what I'm trying to say with all of this is that if you interpolate colors using the OakLab color space rather than RGB color space, you get much better color blending. So this blog post goes through, it goes through everything like that you need to know about this. I've read this blog post a couple of times already. It sets out the entire case for why you want to use that sort of stuff. But all this code is doing is it's just converting from RGB to OakLab colors, which are represented in vector 3s. Then it converts them back into RGB afterwards. So the idea here is that you say local red equals color 3.new 100, local green equals color 3.new 010. Say local, we'll say this is red RGB and green RGB because that's what it is. So we'll say red OakLab equals OakLab dot 2, and this is, we'll give it red RGB. So as the function name implies, this is converting to OakLab, and then local green OakLab, OakLab dot 2 green RGB. Now we can say it's sort of like local blend OakLab equals red OakLab plus green OakLab divided by 2, so sort of get the average color, so mix them together. Then local blend RGB equals OakLab dot from, or OakLab dot from blend OakLab. So blend RGB will then be a color 3, which will be sort of the red blended with green. So if you were to just do red RGB plus green RGB divided by 2, you would get like this color in the middle with this sort of muddy brown. But if you do red oak clab plus green oak clab divided by 2, then you convert it to RGB, you get this really nice gold. So that's basically what oak clab does. So this is useful for like interpolation, it's useful for spring simulation. Basically, oak clab makes it so that a fixed difference in color, like a fixed difference in color, turns into a fixed visual difference, right? So it's like if you step up by a certain number of digits, you will step up by a certain like brightness or a certain amount of color or whatever. Yeah, you can read botterson.github.io/post/oaklab if you want to learn more about that. But this is how Fusion deals with all the colors, because it just makes colors look nicer. Right, so let's start with tween objects, all right? Because tween objects, these are the simpler of the two. So these work a bit like value objects, except they get updated. With like get updated 60 times a second with like a tween, basically. So the way that these work is that you can obviously give it a tween info and you give it an object, and basically whenever the goal object changes value, it will tween towards that new value with the given tween info. So it sort of lets you follow a value using a tween, basically. So this is really useful for transitions and stuff. And so this here is all just setting up the object and a bunch of stuff it has. So you don't need to worry about this too much. This is basically just setting up variables. It's not very interesting. And obviously init dependency for the dependency manager. And of course, because we only have like one dependency, we have to like initialize that too. So here in our update function, whenever the goal value gets updated, we get the new goal value. So say if the goal hasn't changed, then we don't bother updating, essentially. So otherwise we will get our current tween info, and we'll get the value that we'll get our current tween info, and then what we'll do is we'll say, okay, our tween starts at our current value and we're going towards the new goal value. Our tween starts now and our tween will have these parameters, this tween info. And then we figure out how long will our tween be running for. And then we add it to this thing called the tween scheduler. And what this will do, this will sort of connect it to render stepped, and it will just start updating the value of our tween 60 times a second until the tween finishes. Then it will automatically stop. So let's take a look at that. So tween scheduler add, pretty simple. It just says, okay, so just add this tween to a table of all the tweens that we're currently processing. And remove, we'll just remove the tween from the table of tweens that we're currently processing. Then we have this function here called update all tweens. This is run every render step, so 60 times a second. So firstly, we figure out what time is it now. Pretty easy. Then we go through every single tween that we're currently processing, and we get how long has it been since this tween object has started animating. So if the current time is so if we've gone beyond the duration of the tween, then if the tween info sort of reverses back to its original value, then we set the tween's current value to its original value. Otherwise, we set the tween's current value to its next value. All right, so this is basically just saying like, now if we've reached the end, then set the value to the final value, then set currently animating to false, update everything that uses the tween, and then remove the tween from the scheduler because it no longer needs to animate. Otherwise, we'll say ratio equals get tween ratio. This basically, get tween ratio will just tell you how much you need to blend between the old value and the new value at a specific time. So this just recreates like Roblox's easing curves and stuff. So current value, so this will interpolate between the previous and the next value by that given ratio. So it sort of blends between the two. So we'll set the tween's current value to that blend, set currently animating to be true. And then we update everything that uses tween. Fair enough. So let's take a look at what get tween ratio does. So get tween ratio, this right here, if you give it a tween info and you give it a number of seconds into the tween, it will tell you how much you need to blend the old value versus the new value, right? So when ratio is 0, it's like 100% the old value. When ratio is 1, then it's 100% new value. If it's 0.5, then it's 50-50. 0.25 means 25% old and 75% new, that sort of thing. So we're not going to go into this function too much. It just recreates like what a tween info does, basically. So lerp type here, you saw this function as well. So what this does, given a from value and a to value and a ratio, it will return the blended version of that. So this function right here, this is a massive bold function. All this does is this basically, no matter what you give it, it will lerp it. So if you give it a number, it will blend the numbers. Give it C frame, it will blend the C frames. Color freeze, it will blend the colors using OakLab, of course, because all blending should be done in, all color blending should be done in the OakLab color space for those really nice gradients. Color sequence key points, right? It can blend those as well. Date time, if you wanted to blend some dates and times, it can do that too. Number ranges, it can blend those. Number sequence key points, it can do that. Physical properties, it can blend those too. Basically anything that's built up purely of numbers, this function will be able to blend it. So rays, rays is just 2 vectors, and vectors are just numbers, so we can blend rays. We can blend rects, blend region 3s, blend region 3's little brother, blend UDIMs and UDIM 2s and vector 2s, again, vector 3s, vector 3 int 16s. So it blends all of those things, right? This is basically, this is the last lerp function you will ever need. But as a fallback, if the thing you've passed in isn't one of those things that it can blend between, well then it will just say if the ratio is closer to from, then it just returns from, otherwise it will return to, right? So just like switching between two. So that's pretty neat. So that's basically everything to do with tweens. Everything else in this animation folder, so pack type, spring, spring coefficients, spring scheduler, and unpack type is all to do with springs. So we're on the last leg, guys. We are currently 2 hours and 2 minutes into this video. Let's wrap things up with springs. So let's take a look at what springs do. So springs are, they're perhaps the most involved of the animation objects. So here's how they work. So we have a goal state, a speed, and a damping. Obviously you can apply some defaults. So obviously we set up our dependency set here. So if our speed is a state object, we need to add that. If our damping is a state object, we need to add that too. That's basically what that does. And then here we just set up all of our properties. So the way that spring actually works internally is it's not actually just one spring, right? If you have, for example, a vector 3, that's sort of got 3 components to it, it's got 3 numbers. So for each of those numbers, it gives each number an individual spring with an individual position and a velocity and a goal. And what it will do is it will physically simulate each value independently, and then that just packages it back up into a vector 3, right? So obviously we do that. So that's basically what a spring has to contain internally. Everything else up to this point has been relatively intuitive. It's just I wanted to point that out. So init dependency, again, tell dependency manager we exist. Make sure we're adding our objects to the goal states dependency set, or dependent set. What I find interesting is that we don't do that for speed and damping, but I guess we don't need to because that just gets checked 60 times a second anyway. Yeah, that's totally fine. Actually, maybe that needs to be fixed in the repo. I don't know. It's good that I'm checking over this stuff anyway. So self-update. It's basically give us our first value, just the same as we did with the computed. So if we just scroll all the way to the top here, we can now take a look at the methods. We have our get method. So set position, this goes through all of the internal springs that we use for each component, and it sort of unpacks this, like the components of this thing, and it uses those as the positions. So let's take a look what unpack type actually does, right? So this is the unpackaging we were talking about. We just turn whatever you give into an array of numbers. So if you have a number, it's pretty easy to turn it into an array of numbers, right? A C-frame, currently we're using axis angles for this, but we're going to move to using quaternions in the future. So this just decomposes your C-frame into a bunch of numbers. So color 3, that's just RG and B. Color sequence key point, RGB and time. Well, I guess it's not really RGB, it's actually OCLAB, so it's XYZ, but yeah, XYZ and time. Date time is just the number of milliseconds. Number range is just the min and the max. Number sequence key point. Value time envelope. Right, we're just making arrays of numbers. So just unpacking our type into numbers. And so what this will do, so each one of these numbers will then they'll be individually simulated as a spring. Then obviously in the worst case, if our thing cannot be entirely described by an array of numbers, we just return an empty array because it's not, like, we can't represent it. So if we take a look at where has spring gone, spring has disappeared. Fantastic. Okay, so that's what unpack type does. So we just set spring positions to an array of numbers based on the new value. So all of the internal springs will have a new position set by whatever you give it. Velocities, it does the same thing, right? Something important to note, by the way, we are obviously adding it to the spring scheduler, basically to say, oh, hey, our positions or our velocities or whatever have changed, so we need to start simulating the spring again, right? And then obviously update all will happen whenever we change the positions of the springs. We have to call update all because that means that we've changed the value, right? Because the value of a spring object is just, you take that sort of array of numbers and you turn it back into the value, right? You sort of pack it back up. So if you change the positions, well, you're changing what it's going to pack up into, so you have to update all. So then set velocity does that. And add velocity is almost the same as this, except it just creates the array of numbers from what you pass it in. Then instead of overwriting the velocities, it adds on to the velocities. So you can use this to sort of like apply impulses to your spring. And so finally we get on to the big kahuna, the update function. So we start off by getting the goal value for whatever we're trying to move towards. If the goal value hasn't changed, then it means that the thing that has probably changed is our speed or damping. So we just update our current speed and our current damping. And we return false here. I forgot to mention the update function returns true if the value of the object changed, or it returns false if the value didn't. In this case, the value that we return from get here, this hasn't changed as a result of these changes, so we just return false. Otherwise, oh, the goal has changed, right? So if the new goal value is not the same as the existing one, well then we update the goal. We figure out what type of value the goal is now, and then we unpack it into an array. We unpack our goal into an array of numbers, which we will then use as the goals for our springs. We also count how many numbers are in that array that will represent how many springs we need to create, right? Or how many springs need to be internally represented. So if the type of value stored in the goal value has changed, well then we can't animate between types, right? So we just snap to the new goal value. Then we have to set all of the spring positions equal to the goal. We have to do that with like a table copy essentially. The velocities will get set to 0, and so that's what that does. And we remove the spring from the spring scheduler because we are no longer animating it, all right? Because we've just snapped to the goal. So we return true because our spring positions have changed, which means that our current value will have changed. So otherwise, the type hasn't changed, just the position of the goal, right? So if there are no springs to simulate, so if the goal value is something that can't be represented as an array of numbers, then we just snap straight to the goal because we can't simulate it, and so we just return true. Otherwise, if it's animatable, then we just add it to the spring scheduler, and the spring scheduler will animate the spring to the goal. And it returns false because the spring won't immediately just start animating. That's not how that works. It animates every frame. It doesn't just immediately move anywhere. So yeah, so now let's move to the spring scheduler. And let's see. Yeah, so this is the most up-to-date version of this file. Good. So when we add a spring to the spring scheduler, the first thing we do is we say, okay, so the springs sort of, like the last time we added the spring to the spring scheduler was now, but instead of using os.clock here, we just used like the last time that render step was run. And that's just done because it looks better for all of your springs that are started in the same frame to sort of move in perfect synchrony. But you could technically do os.clock here to get the current time. But yeah. And then we set up some internal state. So right here we're just saying, okay, so what's the current, what are the when the spring was added to the spring scheduler, how far was each individual internal spring from the goal? And what velocity did each of those internal springs also start out with, right? And then we add active springs to our table of active springs here, just like we did with tweens. And then here, so update all springs. Again, this runs 60 times a second, as you can see down here. So springs to sleep, this is just going to be a set. So this is just a set that will contain all the springs that we no longer want to simulate once we're done. So this is just done for efficiency reasons. So for every single active spring, we calculate a matrix of coefficients. This is getting into some some calculus, sort of linear algebra sort of stuff, system of equations, blah blah blah. It's just a big pile of maths. But basically, the output of this function will tell you how to calculate the new position and velocity of the spring. So the new position and the new velocity of the spring will be the starting position times pos and the starting velocity times pos vel. So that'll be the starting position, or that'll be the new position. The new velocity will be the starting position times vel pos and the starting velocity times vel vel. Right, so that's all you really need to know about that. I will again show you what that looks like down below. But just if you don't understand this, don't worry, it is a big pile of maths. It is a pile of maths that I did solve on stream though, so that was a while ago. But I did actually solve all that on stream. Anyway, so here we're just doing some aliases. Is moving, so this basically stores is the spring currently moving? So does it have any velocity, or is its position away from like the goal? By the way, whenever I say displacement here, that just means like position minus goal. So it's basically just like, it's like how displaced is the spring's position relative to the goal that it's trying to move towards. Yeah, so then for index goal in iPairs spring goals, so for every single individual spring's goal, we will get the displacement and the velocity. So we're just going through all the internal springs. And we calculate the new displacement and the new velocity using our 4 coefficients up here, like magic. Then, so if the spring is displaced away from its goal, or if the spring has velocity, then the spring is moving. And so we just update the position and the velocity of our internal spring here to our new displacement and our new velocity. Of course, we have to offset it by the goal again. but that's not too big of a deal. So here we say, so if the spring is not moving, then we want to put the spring to sleep. So we want to stop simulating it. So we add it to the set. And finally, down here with active springs, right? So we say the spring's current value is going to be the spring positions, but packed back up into the type, right? So if you look at pack type here, so we just taken an array of numbers and we taken a type. So if it's a number, we just return what's in the array. If it's a C frame, we create a C frame from that array of numbers that we mentioned before. Color threes, then we obviously go back through the OCLAB thing. Color sequence key points gets like, you process the time and the color, and you put it all back into a color sequence key point. Basically, this is all just like construct an object from an array of numbers. And so current value gets set to, the packaged up thing. And then we just have to update everything that uses the spring, like that. And then finally, at the end, every single spring that we no longer want to simulate, we remove it from the active springs table. And, well, there you go. The only thing that's left to look at is spring coefficients. This is pure maths, right? If you don't have a background in calculus, and if you haven't already solved this yourself, this will be nonsense to you. But basically, the mile-high overview of this is basically there is a certain equation called Hooke's law that defines the force a spring experiences in terms of its displacement from its goal, that is displacement from its ideal length, and its spring coefficient, which defines how strong the spring is. You can substitute in Newton's law, which is F equals ma. So you can substitute that in for F. So you have ma equals negative kx. You can add a damping coefficient to the entire thing, which basically it adds air resistance to that equation. And then what you do is you use Euler's methods to solve those equations for position and velocity over time, right? And then this right here is basically just like, okay, for a given time, a given damping, and a given sort of like time multiplier, so a given speed, basically given all of that, how far, like, given all that, like, where will our spring be and how fast will it be moving? That's basically the mile-high overview of that. But yeah, I don't expect anyone to understand this other than me or like Trey. In fact, Trey probably does understand this because I credited him for helping to improve the numerical precision. So there you go. So yeah, so we've gone through everything in the animation folder, everything in color, everything in dependencies, everything in instances. I mean, logging, do you really care about this? This is just logging errors and stuff. I mean, it basically just takes a message from here, formats it, and spits it out. Pass error, this is just the XP call error handler. It basically it creates a proper error object that stores all some nice information and stuff about the error rather than just a string. So we've gone through computed pairs we kind of touched on. Observer, unwrap this here. This is actually, we're going to expose this properly in a future version of Fusion, but all this does, you give it a state object and it will get the value of the state object for you. But that might sound useless at first, but the other thing this function does is that if you give it something that's not a state object, it will just return it straight up. So you could say, for example, local numcoins equals 50, and you can say print unwrap numcoins, and this will just return 50. Because 50 is not a state object, so it just returns it. But if you set numcoins to value 50, well, what this will do is this will get the value out. And so there you go. It returns 50. So yeah, we'll be exposing this in a future version of Fusion. This will be part of a rework that we're doing. But currently it's just an internal function. It's just really simple. And that's all there is to it. So there's value. We've gone through this, gone through cleanup. None. I don't actually think we need this anymore. Yeah, we don't need this anymore. We could probably just delete this from the repo. It's just an object, really. Restrict read. Yeah, there's that. And X type of, we've gone through that. You've obviously seen this is the main file. I think the last thing worth going over is Fusion's typings, I guess. So yeah. So the way that Fusion does its Luau types is it has these big modules full of type definitions, pub types and types respectively. And so these are all just Luau type definitions. And so the reason why we have these big explicit type definitions is because we really, 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 really want you, the user, to have complete type definitions for everything that Fusion has. So if you're doing like a strictly typed project, you can use Fusion still. So this is basically just the precise type definition of everything that Fusion exports. So animatable, this is everything that can be animated by a spring. Symbol, this is basically it's just none. That's what none is. Task, anything that can be cleaned up by the cleanup function. Version, so this is just the version information that Fusion now exports as of version 0.2. Dependency is any object that you can depend on, so like value object, computed objects, that sort of thing. Dependent is anything that can depend on stuff, so stuff like computed or observers and stuff. Then state object is a dependency, and you can get its value, so it has a get function. And then can be state is either a state object of type T, or it's just type T itself. All right. So now specific types here. So a value object is a state object which you can set. And so obviously you have to type T of that as well. So it's generic. Computed is a state object which can depend on stuff, right? It's dependent. And that's all that is. Computed pairs is a state object that contains a table with like keys and values in it. And it can have dependencies, and that's it. A tween is a state object which can have dependencies again, and a spring is a state object that can have dependencies. And we should uncomment these because enable param setters is enabled. Yeah, I think it goes without saying I am working on a in progress part of the Fusion repo, so lots of this stuff still needs to be fixed up. And an observer that is not a state object because it doesn't have a get function, but it can have dependencies, and it does have an onChange function that you can use to add callbacks. Some instance-related types, so a semi-weak ref, as we mentioned before, back when we lost our minds about Roblox's garbage collection. It's just a table that stores an instance, or could store an instance because it might be nil. A special key is a table which it specifies what stage of the instantiation process it runs at, and then it has an apply method which contains all the code that actually applies the key. And this is a type definition for a child. So a child can either be an instance or a state object containing a child, or it can be an array of children, or in general a table of children, right? So this is a recursive definition, so you can have a state object containing an array containing an instance, right? So that's pretty nice. And then property table, it's just your key is either going to be a string or it's going to be a special key, and the value, we don't know what the value is going to be, we don't really care. So that's what a property table does. And so those are all the public types. So this is all stored in pub types, right? So pub types is for all the types that we publicly expose to the user. Then types contains everything else. These are all the types that are used internally in Fusion, but which we don't expose to the user, or shouldn't expose to the user. So we have the none type, which again, we don't really need that. Error, so this is the type for like an error object as returned by parse error. So then we have all the specific types. So the state object has an internal value field. Computed has internal values, callbacks, and old dependency set. Computed pairs has all that stuff. Tween has all that stuff, and Spring has all that stuff. Basically, these internal types, like, they're the same as the public type definitions, except they contain all of the private members. And then, of course, Observer has change listeners and stuff. Yeah, easy peasy stuff. So that's what all that stuff does. Yeah. And I think that is actually every single code file in Fusion now explained. So yeah. So this is basically just a big brain dump of like everything I know about Fusion. And hopefully this helps you out if you want to be a contributor. This should help you get your bearings. It is worth mentioning that lots of this stuff I am looking to simplify, right? Stuff like the dependency manager I am especially looking to get rid of. Like in version 0.3, we are going to be replacing the dependency manager with a much simpler system that will be much easier to understand. No more stacks of stuff. No more like init dependencies and capture dependencies and stuff like that. Yeah, and we're obviously replacing computed pairs with 3 new objects. The joy of that, right? But yeah, we are genuinely working on all of this stuff. It's all in progress. It's all early beta. But it's all now documented in a YouTube video. So thank you guys so much for watching. If you watched this entire video, I am so sorry. but yeah, hopefully you learned something. I've been Dan, and I will see you guys next time. Have fun.